Okay, let's dive right into this. Welcome to today's Explainer, where we're going on a seriously mind-bending journey into the future of material science. We're looking at a concept that completely redefines how we build, well, pretty much everything. If you're into discovering how cutting-edge research is pushing the absolute boundaries of what's physically possible, you are in exactly the right place. So I want you to really think about this for a second. What if a spaceship could literally heal itself? It sounds crazy, right? I want to hook you immediately with this sci-fi premise because it totally forces us to rethink what a structure can actually do. We're so used to thinking of structures as these static, passive things. A rock hits a ship, the ship dents. A crack forms, and it just spreads. But what if we challenge that entire assumption? What if a structure didn't just passively take a hit, but actively responded to it?
It's kind of like Black Panther's suit. Think about it. Kinetic input, like a punch, a bullet, some kind of massive impact, hits the suit. But instead of just sustaining damage, that energy is absorbed, it's converted, and then it's used later for defense or even healing. This logic model flips our whole understanding of physics right on its head. Instead of an impact just being this catastrophic event that causes damage, the material itself turns that kinetic energy into a distinct advantage.
Which brings us right to Section 1, From Fiction to Reality. And to understand how we get there, let's look at Section 2, The Evolution of Structures. While a self-healing kinetic suit sounds like pure Hollywood magic, it's actually grounded in very real, rapidly advancing composite architecture. We didn't just wake up one day and decide to build this. There's a really fascinating historical progression here. Walk with me chronologically through these breakthroughs. So pre-2021, the big leap was moving from a passive structure to a monitored structure. We added sensors to detect damage, basically giving the structure a nervous system so it could feel strain. Then, moving from 2021 to 2024, we saw the rise of self-healing structures. Using intrinsic chemistry and microcapsules, materials could actually recover from microdamage all on their own. By 2025, the focus shifted to multifunctional energy harvesting. Could a structure sense, heal, and manage heat or generate power from vibrations? The literature said yes, absolutely. Which brings us to 2026 and beyond, the computational craft, a structure that actively interprets its environment and adapts on the fly.
But, there's a massive engineering hurdle here, balancing reinforcement with mobility for healing. According to a really comprehensive 2026 nanocomposite review, this is the ultimate tightrope walk. You see, excessive reinforcement can suppress the material's internal mobility, which totally tanks its ability to heal. The material can't just be more hard or more smart. It has to exist in this beautifully, carefully tuned intermediate regime where strength, conductivity, and repairability all perfectly coexist.
So how do we achieve that perfect balance? Let's get into Section 3, Enter the Craft. If researchers can actually nail that careful material balance, we're looking at the ultimate solution to aerospace engineering's biggest flaw. Traditionally in aerospace, we build completely separate systems for absolutely everything. One material bears the load, a totally different one houses the sensors, another stores battery power, and yet another manages the heat. It's entirely segmented. But in this new paradigm, the craft is one integrated, organism-like platform. This new philosophy entirely collapses all those old boundaries into a single, unified body.
Let me officially introduce this concept by Luis Manuel Ortiz Inostroza, the craft. He defines it as a self-aware architecture developed as a distributed computational material system that converts impact, stress, and environmental load into protection, power, and repair. I really want to emphasize that. The structure itself is processing its own survival. It doesn't hand off the job to a computer in the cockpit. Actually, scratch that. The hull is the computer.
Let's look under the hood to see how this is built. Section 4, the ultimate material stack.
This isn't just a theory, folks. We can break down exactly how this platform is constructed physically, step by step. Step 1 is your outer impact layer. This is a super tough composite skin designed just to spread physical force and resist punctures. Step 2 is the conversion layer, which uses piezoelectric materials to actively take that physical deformation and turn it straight into electricity. Next up, Step 3, a thermal management layer, using thermoelectric materials to harvest and regulate the resulting heat. Step 4 acts as the self-healing matrix, deploying epoxies and polymers to automatically close up microcracks and restore structural integrity. Step 5 embeds compute and sensing via distributed nodes, tracking the power flow throughout the whole system. And finally, Step 6, a storage and routing layer acting kind of like a buffered battery, retaining all that harvested energy for later use. And if you're wondering if this is completely science fiction, the research actually points out every layer already has partial support in the literature. But the unprecedented part is their orchestration into a single, self-adaptive craft. I really want to highlight the credibility of this concept for a second. Every single one of these components already exists in isolation in a lab right now. The absolute genius is bringing them all together into a single logic chain: detect, interpret, harvest, store, heal, and just keep operating.
Which leads us to arguably the most exciting part. Section 5. Full body computation.
This flawless integration leads to the most awe-inspiring aspect of the entire concept: continuous, distributed computation happening within the very atoms of the ship's hull. Because the hull is acting as a sensor, a battery, and a processor simultaneously, it can perform predictive load management. It offers adaptive shielding. It can instantly do fault localization, manage mission-aware energy routing, and execute real-time resilience optimization. The craft doesn't just survive a strike, it literally learns from it. It translates that strike into a usable electrical signal and entirely reconfigures itself around that specific event.
So the big takeaway here, the craft treats strikes, heat, vibration, and stress as information and resources, not just threats. This is exactly why this matters so much. The structure is no longer just built, it is computationally constituted. It is actively computing with the world around it.
Which leaves us with this final, massive question. If our structures become self-aware, what on earth do we build next? If the walls, our ships, and our cars, and eventually our everyday buildings can feel, heal, and compute, the limits of human innovation are truly endless. Thank you so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.